Okay. So I'm supposed to talk about Jovian weather, and I like to think of myself as a theorist and a computationalist, spherical cows and things like that. But I found myself getting into really looking at data. Because the red spot is everybody's favorite spot, and everybody sees it exactly the way they want to see it. So I went to a conference here about 10 years ago. Oh, the red spot's a solitary wave in a soliton. No way. If you look at the data, can't possibly be so. Okay, so this is a picture that was taken from the Hubble Space Telescope. You see the great red spot sitting here at about 23 degrees south latitude. That's about 26,000 kilometers by about 15,000 kilometers. Slightly smaller over here. This used to be a white oval. It turned red in December of 2005. That black thing is the reticulating arm of the Hubble Space Telescope. I like this picture because as a theorist, I'm really proud of it. I took it myself. I applied for the Hubble, took it, and got it. All right. There's a lot going on here. Okay. I left the lens cap on the first time. Listen, is there a pointer in here?
There should be one on the table.
Oh, here we go. Got it. Okay, so there is weather. There are changes. This is 1998, a very quiet time, especially in the equatorial latitudes. You see the red spot. Something interesting is happening here, which we'll talk about. I actually wrote a paper in Nature that said there was, due to an event that happened in 2000, that there would be an upheaval. Red spots and Jupiters go through upheavals. The picture in 2000, this is a very different looking planet. 2007, the equator is really, really active. Stagnation points with material leaking from the equatorial regions into the more southerly regions. There's just a lot of activity going on here. It's not a constant planet. The year is missing on here. This was 2 years ago. Here we go. A lot of data is taken every night by amateur astronomers. Here, a missing stripe, right? That's a big change. Last month, Amy Simon and NASA released a press release. Jupiter's red spot is mysteriously shrinking, right? It's getting smaller and smaller. What's happening here?
Climate change.
Climate change. You bet. It's climate change. Okay, so Jupiter is a planet in the weather layer, which is where we see the clouds, which is about 100 degrees absolute, and it's just below the tropopause, which is at about a tenth of a bar or so. What you see is zones, stripes, right? So these velocities, which are measured by LeMay shortly after Voyager, their characteristic velocities are 100 to 200 meters per second. They oscillate back and forth. They're wider at the equator, then they get narrower and narrower at the poles. As Brian here? No. As mentioned, the westward jets are smoother than the east ones, are more peaky. The way these data were collected was you basically took a line of pixels from the camera and you took another picture later and you did a correlation moving the whole line of pixels over to find out what the displacement was. You divided by the time, and that's how you got these velocities. You can do a little bit better today, but that's not bad for 1986.
And that's constrained to be only a zonal motion, or is it a 2D correlation?
This was only, the way this was done is only a zonal motion. They took lines of pixels and looked for the correlation and the shift. We'll talk about other ways in a bit. This is, right, people didn't know what the red spot was. Oh, it's a floating iceberg, it's this, it's whatever. But we really got data, velocity data, finally in 1979 when Voyagers 1 and 2 went by. So this is the red spot. You can see it's a pretty big object. It spans a lot of longitude, about 26,000 kilometers. And again, here it's about 20 degrees, which is about 18,000 kilometers here. Typical velocities in the red spot in the east-west direction, about 100 meters per second. North-south are about 50 meters per second. But it's pretty sloppy. This is from the Voyager 1 and the Voyager 2 flyby. Put all that data together. What you do was you take a graduate student, you put him in a room, a darkened room, and you give him an illuminated picture of the clouds and say, all right, figure out where that piece of cloud moved, 10 hours later, right? Because the planet is, Voyager didn't orbit, right? It was a flyby, so you have to wait 10 hours before the red spot pops up again because it's a 10-hour day. And so 10 hours later said, I think that cloud moved from here to here. Okay, great. So you put a little velocity vector over there. You divide by the time. You put the velocity vector between where you saw it and where it ended up. And you got about 2,000 of these guys. These guys have about a 10% uncertainty. Maybe 10 meters per second is probably uncertainty in these velocities. And I'll go into a bit how I got those. But the real problem with this is the sparsity of the data. Right? If you've got this big a domain, right, you really want to start looking at the data and doing things like U double prime minus beta. You want to calculate vorticities. You want to, do things with that. Okay, but before I get into that, right, so basically 12 eastward going jets, 12 westward going jets, typical velocities, red spot. 3 white ovals merged to 1 red oval around the last millennium change. It's claimed that 90% of the vortices are anticyclones at turbulent velocities about 2 meters per second.
And Phil, are we confident that those clouds are tracers?
No. Thank you for asking. They definitely have problems. And I'll show you some of those. Are the long-lived cloud vortices? Are there vortices where there are no clouds? Can there be, there are a lot of questions. People like to look at cloud morphology and deduce things about dynamics. Okay, manual tracking. So these are 10-hour pictures, taken apart 10 hours, and you plop down the velocity. You get about 1,000 of them from both Voyagers. There's just too few. So what people really wanted to know was if I take, right, here's my red spot going around, and I take a slice of the major axis. So this is the east-west axis going through the center, all right, and you take all the data that was known, the north-south component of velocity that was in 3 degrees, which is a pretty big number of that axis, and you plot them here, you only get about 100 points. And it's even worse if you look at through the minor axis, the north-south axis, and you plot the east-west velocity, you get about fewer than 100 points. People take their careers, right, their theses, their everything, is fitting velocities through here, right, and estimating what the peak velocities are, and then, wait for it, differentiating and get the vorticity or U prime, and then wait for it again, really getting U double prime. They have to take the second derivative of data that's this noisy and not equally spaced. That is a very tough business. I would estimate that the uncertainty in the vorticity you get here is about 60%, and the second derivative is order unity. Okay. All right. So I want to talk about, of all things, I got into data analysis, right? Because the theories needed better data. So here's the result of the data analysis, and I'll show you how I did it. So using a different method of extracting velocities from the clouds, which may not be tracers, but we went back to check, right? Instead of getting 1,000 vectors, we got 1.6 million for the red spot. And each vector had about 3 to 5 meter per second uncertainty. I couldn't plot 1 point. It would all look black if I did that. So this is only 10,000 of the 1.6. If I go into the little corner over there and plot the data, right in that corner over there, so this is about 0.2 by 0.5 degrees. So that's about 200 by 500 kilometers. The pixel size on this guy is about 150 by 150 kilometers. This is how many points. I plotted every point in that box. So you can differentiate this stuff. One of the things you want to do when you differentiate randomly scattered data, you are in serious ill-conditioned trouble if you can't first put that data onto a uniform grid. All right? And for that, you've got to oversample typically by about a factor of 10. So there's lots of stuff. People start with splines to do this and then work their way forward. But to try and get to differentiate this stuff is a lot of work, and you really want to oversample. Okay, so if I look at the major axis of the red spot, these are the kind of velocities I get within a half a degree. Lots and lots of points. Though there's some missing within half a degree, they're going to be bold spots. But that's a pretty good velocity field for the red spot.
Can you go back 2 slides, please?
2 slides, okay.
One more. What happened to the turbulence on the west side?
That turbulence that is up here. And also, the turbulence is cyclic, right? In fact, when this picture was taken, it was at a very low state. It comes and it goes, and nobody really understands why. This northwest turbulence is a very funny thing. To a lesser extent, there's turbulence down here as well.
And it comes down, I guess.
Yeah, right. So we're entering a very turbulent state right now. Good question. And that thing that was red, which is called the oval BA, the little smaller vortex on the first slide. Again, this is through the principal axis. I used Cassini data from 2000 and Hubble, which we took in 2006 from those pictures that I showed you. And there's about a 3 or 4 meter per second uncertainty here, but the velocity has not changed really beyond the observational. And this is important because people, when the oval turned from white to red, people wanted to have all sorts of reasons. A lot of them dynamically say, oh, the velocity's doubled or tripled. No, the velocity is not doubled or tripled. It's really quite solid on this one. Okay, so how did we do this? Okay, so let me see. I'm going to try and use the sideboards here. Okay, I got into this game by being a nasty person and arguing with an observer that I felt that their estimates for the uncertainty and the velocity were too small. Because the way they put their estimates on the velocity was, they said, look, we've got pixels about 150 kilometers. We're taking the picture every 10 hours. Therefore, you take 150 kilometers, divide by 10 hours, and that's the uncertainty and the velocity. I said, no, no, no. The velocity is a convolution of everything that could have gone wrong. And if you'd left the lens cap on the camera, you would have recorded the same thing. I said, look, I've got 2 ways of measuring velocity errors. So one way is, as a numericist, as a computationalist, one thing we really know how to do is we know how to solve the 2-dimensional advection equation to arbitrary accuracy. So suppose I have a cloud intensity, and so some intensity of those clouds that are being reflected as a function of position and time, right? I can solve this equation, partial with respect to t plus velocity. If you give me a velocity, dot gradient, the intensity is equal to 0. So if you give me the intensity at some time, and if you give me what you think is the velocity, I can advect it from one time to another. So here's what I did. I said, all right, you have to know about correlation finders. A correlation finder is back in the late 70s, the way people in the laboratory measured velocities was they put in passive tracers. They did laser sheet illuminations to have 2-dimensional plane, and then they did exactly what they did here. They watched the tracers go from place to place. But then they decided that wasn't a good way to do it. So they had all these great CCD array cameras, and so they had pixel fields of about 1028 by 1028. And so they took the pixel field with all the tracers in it. And what they would do is they would take some subset, some box of some pixels here, and they'd have another picture that was taken just a little bit later, and they'd say, okay, I'm going to move this box either up, down, sideways to some location until they found the maximum correlation of this box. And then they did a little shift, and then they had sub-pixel accuracy, so they would shift this pixel a third or quarter of a pixel away and do it again, and they could get millions of velocity vectors. And that's one method is called particle image velocimetry, another one's called correlation image velocimetry. And that's the way that we typically do in the lab. So what I did was I took their velocity field at one time, then 10 hours later vectored it, and looked for correlations, and the displacements were huge. I took those displacements and divided by 10 hours and said, that's a more accurate representation of the velocity errors. But then I realized, hey, you can do even better than that. So what we did was, it turned out Paul Diamandouros down at Caltech tried this on the Voyager data and was not able to get correlations. But people then tried it a little bit later with snapshots really close together. People were able to find correlations using an automatic correlation image velocimetry finder if the separations between the images was really, really small, less than 41 minutes. But the problem was they had a displacement that was very small, and they had a time step that was very small, so their velocity was 0 divided by 0. You get big errors, but at least you could find correlations. So what we did was the following. Hubble goes around every 90 minutes. right? Half that time, the Earth is blocking our view of Jupiter, so we can't see it. So we got about a 45-minute window to get two snapshots. So we did that. We took images 40 minutes apart. We took two images of the red spot and oval, 40 minutes apart, and we used this automatic correlation finder, CIV, correlation image velocimetry, and we were able to find correlations. And really small displacement, really small time, and we got a really, really ratty-looking velocity field. This is the velocity field that we got. It is not, this is through the principal axis, where it's supposed to go up, down, really bad. Through the north-south axis, it's pretty rotten. But we got about 1,000 images. Then we waited. We waited for Hubble to go around a few times until it was about 10 hours later, so the same vortices were below us at one Jovian day. And we took another pair of images 40 minutes apart between these two guys, and we got another really ratty velocity field. Okay. Just as bad as that. So then what we did was we said, okay, let's take these ratty velocity fields. Let's go 5 hours. So this is 0 hours, this is 10 hours. We took this ratty velocity field, and I vectored it, two-dimensional advection, 5 hours ahead and got an image. And I vectored this guy 5 hours behind to get an image of clouds. And then I put it through the correlation image velocimetry. We found over 2 million hits of correlations. So now you undo that using the same ratty velocity fields, and now you've got a Rosetta Stone. You know that this guy over here is secretly correlated with that point over there. And so now you can take those velocities and use those, and you can build trajectories. So you can have, say, an image here at 0 hours and 10 hours, and now you can iterate on that. So here's a particle that's supposed to be, it's supposed to end up over here. So you go and you vector through space and time, and it doesn't quite end up there. It ends up here. And you take this guy and put your negative velocity field, and you vect him backward in time, and he doesn't end up here. He ends up here. So then what you do is you make a little, like a ladder out of this, little tie points in between, and you linearly interpolate. And now I've got a synthetic trajectory that takes me from where I want to be to where I want to be. And I break that up into velocity fields. And I augment my velocity set. And what I do is I augment and throw away. So there's a second way of measuring uncertainties in these things. As I said, when you have a uniform grid, if I want to advect something with a velocity, right, generally I want to have a uniform grid, because if I'm advecting a cloud or a particle from here to here, right, I need to be off the grid, and I need to interpolate. Interpolation is fast, well-posed, accurate. But generally, when you do this correlation image velocimetry stuff, your particles are random, right? And you want to go from random points to grid. And that's ill-conditioned, and you've got to oversample. So what we did was we basically created the grid velocities from the scattered velocities, and then we interpolated back to where one of the random velocities was. And when we interpolated, if the velocity wasn't very close, we'd throw it out. So we had a discriminator. We had first of all, by measuring how far apart they were, we had to measure the error. But also, we could decide which individual velocities were spurious and shouldn't use. So we did this about 10 times back and forth, back and forth, back and forth, and until it kind of didn't get any better. And both measures of error, both this one and when I go from one image to another image 10 hours away, they both give me errors about 3 to 5 meters per second. We've been cleaning that up. We started at 5 meters per second. We're now down to about 3 meters per second. So having the velocity is a really nice thing to do.
So what is your effective resolution then when you get back to this at the end? You're throwing away things by mismatches, so there's some sampling issues around this interpolation versus grid scale. So do you believe the velocities are on the grid scale are actually an average of over that cell?
They're a local average over there, and I really think those velocities on the grid have about 3 meters per second uncertain, just because when I do that full thing of advecting with them, I end up really where I want to be. Let me show you an example of that, a qualitative example. So you've probably seen movies like this all the time on NASA's website. This is a white oval about the time of the Cassini flyby, because it had a very funny stagnation point there. And when you go to the NASA website, right, basically they snap a picture every 10 hours, and so they make this nice uniform-looking movie, and each frame here was taken 10 hours apart. Okay, so what we did, this is a snapshot of an oval at basically time 0, and we had another one just 10 hours later, we used our velocity that we created, and using the velocity that we created, we're not taking these every 10 hours apart because we only have 2 images. With our velocity field, the first frame really smoothly goes into the last frame of this picture. So it really qualitatively meets the bill of what we did. So that is our method of collecting velocity fields. You can do the same thing for the east-west winds. You can see how much jitter there are in them. Instead of moving a whole line of pixels across, you actually calculate the winds, and you can find out what the standard deviation is in longitude and in time. And the winds change the function of time. Here's 1997. Here's from what we did with Hubble. There's some bald spots here, but there's some changes in the wind velocities, right? And they're not really smooth things. They don't fit some nice, like, they're problems. They're not quite u double prime minus beta, right? So when you look closer at the things, you find that there are differences. So the first part of this talk, I'm going to tell you about quasi-geostrophic things. We've heard a lot about quasi-geostrophic things. I'm going to tell you about using an analysis, an inverse method, and some things you can do with quasi-geostrophic models. And then I'm going to do 2 problems at the end that are beyond quasi-geostrophy. You couldn't do it with quasi-geostrophy. And those have to do with the white oval turning red, and it has to do with the longevity of the red spot. So this is your standard 1.5 layer model. I've got some bottom topography, HB. I've got some free surface height, which is a function of x, y, and t. I've got a Coriolis parameter, constant g. I've got some horizontal component of velocity. I've got my potential vorticity just being advected along. My potential vorticity has a deformation radius associated with it. What else? It's got a bottom topography, and it's got the usual stream function.
What about beta?
Pardon me?
Beta.
Oh, yeah, there should be a plus beta y over here. Sorry, I forgot that. Thank you. I'll just put it in with chalk, plus beta y. All right. But the problem is that when you're doing these problems, you don't know what the deformation radius is. You have no clue if there's a effective bottom topography from some dense layer below it or not. And you really don't know what the PV is. And the problem is with zonal flows, if I have a steady zonal flow where partial q with respect to t is equal to minus v dot q, if q is a function of only the meridional variable y, and it's got a unidirectional flow, then everything's a solution. There's a total degeneracy there. So you've got to come up with some other way of doing it. Now, people have looked for bottom topographies by taking second derivatives of the velocity and assuming that the PV along closed streamlines is constant, but it's tough to get that stuff. It's very ill-conditioned. So I'm going to tell you a slightly different way of doing it. So let's see, I'll try this on the blackboard. If you look at a spot, an oval, a red spot, whatever, right? So here's my east, west, north, south direction. You get a bunch of closed streamlines typically, and then you get a bunch of open streamlines. You may get stagnation points where things turn around or whatever. Okay, so I'm going to look for solutions of this form. And the way I'm going to look for solutions of this form is I want to find quick solutions to this problem, because what people typically do when you have unknowns like the deformation radius, PV, and a few places, what they do is they do, quote, an inverse problem. They'll take their favorite initial value code. They'll put in their best guess at what this stuff is. They'll turn it on and let it run. You've got problems with dissipation, but forgetting that, it eventually comes to equilibrium, and they go, nah, that doesn't quite look like the red spot. Let's try another set of parameters. Well, for these guys to equilibrate, right, because you have to do with your current condition limited typically, it might take you 20 to 40,000 time steps. And so typically in papers, they might look at 10 parameter values. Right? This, I want to do a relaxation method. I don't want to iterate. I basically want to take my step and do it 10 times and converge. And then I'll be able to look at tens of thousands of parameters. Okay, so the thing that is kept constant here is, for all the open streamlines, right, I'm going to consider this like a contour dynamics method. I'm going to represent lots and lots of contours going across this way, contours in here that are closed. So I'm going to do contours of PV, if you will. And for the open ones over here, I'm going to specify at this end of the boundary what the jumps in all the contour PVs are. And over here in this spot, I'm going to tell you for each contour that I'm going to put in here, I'm going to tell you what the jump in the PV there. So I'm going to, my set of variables that I'm going to test in my inverse problem is all those values of PV plus what the deformation radius is, plus also what the velocity of this is compared with the frame I'm looking at. Because I want to be in a frame where it's steady, so the surfaces of PV and the streamlines are the same surface. Okay, so the way this works is the following. This works surprisingly well.
Are you saying that you can kind of estimate the change in vorticity following the streamlines, and then they use that to infer you're assuming PV's constant along?
That's not what I did. That's what Dowling and Ingersoll did for Dowling's thesis. Okay. And he has to take the second derivative of that very, very noisy Voyager velocity.
Or but from this, it looks like you could almost, well, the way you drew it anyway. Yeah.
No, okay, so I'll show you what I'm going to be.
I'll let you, sorry.
Okay, let me show you what I'm doing, because I'm not going to assume basically much of anything. I'm simply saying, okay, look. Let me think, okay, I've got some zonal flow that kind of latitude spans where the red spot is. So let me do contours along there and say, okay, for the unperturbed zonal flow, right, there's some PV. So there's value Q1 in here, then there's a jump of PV Q2 here, then a jump in PV3, QV4. And I'm not saying these guys have to be monotonic or anything. It's just, I'm going to discrete. And then I'm going to say, oh, I'm going to add to that, right, a spot. So the spot also has closed contours like this, and there's, QA here, QB here, QC here, and so on down the line. So I'm going to just superpose these two as my first guess, and so I get things that look like that. Well, that can't possibly be a solution, because if it were a solution, the streamlines and these contours would be coincident, and I can't have streamlines with themselves. So that's my first guess of the PV. So then I say, oh, I need a stream function. So what I do is my stream function obeys a Helmholtz equation. So my first guess at the stream function, and then I've got some inhomogeneous terms over here, which is my beta, my bottom topography, whatever, right? That is equal to my first guess at the PV. Well, if I'm doing this spectrally in doubly periodic domain, this takes 1 instant to compute what the streamlines are. The streamlines don't have this weird property. The streamlines look kind of sensible. The streamlines look like a bunch of nested things, and then they deform the streamlines from the zonal flow. Asymptotically far away, they're the same, but basically they're deformed around it. And then I choose my streamlines. I say, okay, I want my suppose I had initially said, oh, I want to have along here, I wanted to have my jumps in potential vorticity be at these points, and I want them to be a certain amount. I calculate the stream function through my places where I wanted PV things, and I simply paint. Inside this one, I paint it with QA. Inside this one, it's QB. Over here, it's QC. And I do the same thing right for where I pin down my open streamline. So it's going to have the same PV structure as before. And then that's my next guess at the PV. And then I just invert. Well, to make a long story short, the process converges very nicely. Here's this first lousy method where you can see there's shades of gray here. I've only just for pedagogical reasons only used 3 of these guys, and 1, 2, 3 of these guys for the vortex. Right, those PV contours intersect. All right, and then so I go and I calculate my psi and then repaint my PV so that it matches at these points and these points over, or those points over there. That's my first iteration of the velocity field. So you can do that 0th iteration, 1st iteration, 2nd iteration, 3rd iteration, 4th iteration, and by then it's basically converged. And you can do this with hundreds of PVs, hundreds of contours, and get your spots. So it converges very quickly. It's a very fast solver. But if you use fewer than a few hundred, right, it's going to converge in about 10 iterations. And so now what you do is you say, great, I got a fast solver, and let me just start guessing like crazy what the jumps in all those contours are and what the deformation radius is. Shove it into a genetic algorithm, which is a great algorithm. You've got non-convex problem to work on. And it, have you ever guys used a genetic algorithm to search for something?
Diffusion in this problem?
Pardon me?
Diffusion.
There was no diffusion in this problem.
Why? There's lots of diffusion in. Yeah,
because
it's like this.
No. Because the point is, I am looking for steady state solutions to the problem. To first order, right? We're looking for steady state solutions to the problem. No, I'll talk later about forcing and dissipation. But to first order, we're looking for steady states of non-force, non-dissipative systems. Right? We want to compare all possible ones we could think of that obey the steady equations with no force and
I've seen lots of
dissipation.
movies of the great red spot. It looks like the thing's churning like that. It must have a lot of eddy dissipation.
We'll talk about that in a moment. All right, bear with me on this. This is going to be no dissipation, but we will get to that. Okay, so basically, just kind of the way this goes, this is like for the oval. So if you start off with just no contours here and just tell me one oval for the PV, it's actually not such a bad fit. This is comparing the data, this dashed green line, with the analytic solution that comes out of the equilibrium solution here. It does a lousy job matching the velocities at the end. But you start putting in contours here, and you can start doing better. You put more in, and you do better and better and better. The same thing for the red oval, right? If you just make one contour, you won't get, this is the analytic solution with, right, it's uniform PV inside. It's much more uniform velocity, almost zero in the center. You don't capture that at all. By getting the deformation rate, you capture that. By getting the boundary location here, you capture where that peak is located. But you do a lousy job in the east-west direction. So you put in another contour in the center, and that can start to really flatten things out. So if you want to flatten things out, you put more and more contours in the center. If you want to make matches better in the east-west condition, you start putting more and more contours in this. And you put enough contours in. All right, as I said, I can measure the uncertainty and the velocities that I'm trying to compare to. Right? I can get the difference between my analytic steady-state solution and those observed velocities within the 3 to 5 meters per second. Right? So I can get within observations.
And your contours here are part of the genetic algorithm, so that's not something you put in the beginning. That's something that comes out of what fits well. Right?
I tell it how many contours I want to use, and then it assigns at every contour what the jump in PV is.
Right, because that's where the mixing part comes out. Because whenever you've got a bunch of mixing, you just put that inside of a contour and you don't care.
That's right.
You homogenize it.
Yeah, right. So then you'll have a whole bunch of contours where there's not much change.
Right.
Right. So this but the point is you're always comparing steady state solutions, right? Which is what we wanted to do. All right. So you learn some things right away. First of all, the incredible shrinking great red spot in oval. These are some streamlines. This guy over here is basically the last bit of PV in the oval. Right. So the oval as a dynamical system is got a bunch of potential vorticity, right? There's effectively none outside here. This has no correlation whatsoever with this cloud cover. So if this cloud cover is decreasing, that doesn't tell me anything about what the PV is doing. For the red spot, same thing. Here's basically the last PV, stream function where there's any decent PV inside of the red spot, and the cloud cover is bigger than that. So if the cloud cover is getting bigger or smaller, it might not tell you anything about the dynamics of the PV at least. So you've got to be very careful when you talk about that. But if you do look at the PV, there is some shrinkage in the PV. This is the major outside diameter between 96 and 2000. It's going down a little bit. We got the uncertainties by doing bootstrap Monte Carlo on all these things. So when you do all these fittings with the contours, right, when you're done, you go, I've got a number. I want to know what the uncertainty is. So the way you do it is you go in there and you randomly sample half the data that you had. And you use that, and you come up with a number. And then you go in and randomly sample using another part of your data. And you do that several times. And the scatter in that is where these guys come from for the bootstrap Monte Carlo. So it's a fairly objective way of getting uncertainties. But there does seem to be some shrinkage going on. Let's go on.
And it's the deformation. You got a deformation radius
right.
for that as a side benefit, I guess.
Right. So at the red spot, it's about 2,000 kilometers plus or minus. I can't remember. Was it 100, 200?
Do you get an equivalent depth? I mean, does that automatically follow from the deformation radius, or how do you?
Let's see. So when you have a deformation radius, you can write the deformation radius. You don't really get an equivalent depth on that, right? All you're going to get is G and N and.
You don't know what your N is, yeah. but is there anything? Are there independent estimates? I'm just curious about your view on the vertical structure.
I will get to that, but there I can't. That I'm doing with Busanesque. Okay, so 3D. Yeah.
So in this convergent procedure, how many free parameters do you have? I mean, I understand that you have one free parameter for each annulus of.
Okay, so we have the deformation radius, we have the velocity, and you have all the values where basically twice the number. Okay, you've got the latitudes where you can put the open contours. You've got the values of the potential vorticity jump across there. We generally smear these out a little bit because we're putting into a spectral code, so we use a tangent profile jump, so we can smear that out as well. And then for the same in here. So typically, we easily can run with a genetic algorithm a couple hundred parameters. But generally, you don't need that many. So I wanted to say some things that we were talking about earlier. I wanted to talk about staircasing effect, right? The Phillips effect, and they found in the ocean where he looked at salt density in the upper layers and found it made a nice staircase. So there have been a number of papers by some of the people who I think have already left for the most part, unfortunately, here, about staircasing. So there was some question about whether the PV should form staircases, the zonal PV should form staircases. And, and going back to Brian, this is an example of, this is exactly the kind of flow you criticize. Box, small scale forcing, beta. This is what the velocity, this is what the velocity looks like. Makes these kinds of open parabola guys looking here. And this is the PV as a function of y, and it kind of staircases. All right, so the question is there staircasing going on in Jupiter? Because a lot of people suspected it might.
Different model? What is it?
Pardon me?
What is this, a different model? You're doing
No,
something?
okay. So what this is simply a QG box, doubly periodic, right? Flat bottom, no bottom topography, put in a beta. Put in small scale forcing in a ring at the smallest scales. Put in rarely drag at the largest scales. Turn it on, let it come to statistical equilibrium. Plot all the different lines you hear are, this is one instant in time, but equally spaced in longitude plots, and they all kind of lie up on each other, so they're fairly zonal. So this is the east-west wind as a function of latitude. All right? And as the same latitude scale, here's the PV that came out of it. And again, there are many, many different lines all superposed at different longitudes. All right. So that was the motivation. Okay, right. The idea behind monotonic staircasing makes sense, right? If I just had vorticity and beta y, right, and I had no flow, then I'd have a linear PV gradient as a function of latitude. But the idea is, right, you've got stirring, you've got vortices at different latitudes, and these guys are going to stir these guys up, and this will make this flat, and it'll connect, flat, flat, right? So that's the basic idea about PV mixing. All right. Didn't happen. If it had been a staircase, this is latitude from minus 35 degrees to minus 10 degrees. And this is basically what our PV looks like as a function of latitude. Instead of going, it goes huge step backwards. These PV gradients were gotten by our best fit to the red spot and the oval, right? Because when you do the zone of flow there, you get the bottom topography, which is equivalent, if you know the velocity, to the PV. So, so a couple points here. That's the backward step. Here's the red spot. And so what we expected to find was at this eastward going jet there, we'd expected to see a jump in PV like this. The oval is sitting down at these latitudes, and so we expected to see a jump here at the westward jet, no jump in PV, and then another jump over here. But this one, this is the jet that's going around here, goes around the red spot, asymptotically goes out there, and it's got the PV jump in the wrong way. So this was based on our...
Not the zonal mean.
Pardon me?
That's not in the zonal mean, sure. That's not in the zonal mean, is it?
I'm sorry, what? No.
This PV is a cross-section through the spot.
Okay, so the red spot, yes. So if I look at a westward going jet at about 20 or so degrees latitude, right? So here's this wonderful jet that you see going in. And it would intersect the red spot about a third of the way from the top. And it's bent around it. So yes, this PV is the PV out here far from the red, many deformation radii away.
But I mean, basically, it looks like the PV is decreasing away from the center of the spot in this cross section. Isn't that?
That's entirely what you'd expect, surely.
Well, okay. So if people out here far from the spot,
Well,
if you expected, boom, 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 that's not what you're
You
getting.
have enhanced PV in the spot.
No, this is not the PV in the spot. This PV is the one that's asymptotically far. And it's easy to do asymptotically far because just go 5 deformation radii and everything decays exponentially with the deformation radius length scale. So this is asymptotically far from the spot, this PV. Okay, so that's bad news because everybody expected something different. Not very satisfying. But there's 2 qualitative measures that says this is where to one. And let me tell you what those 2 qualitative measures are. So back in the early 70s, Moore and Safman at Caltech wrote a paper on 2-dimensional vortices embedded in shear. Okay, so you've got a uniform shear flow and you've got a uniform patch of vorticity. You can show very simply, a nice little exercise for first-year graduate students, that the equilibrium is an ellipse. And this aspect, this is my x direction, this is my y direction. The aspect ratio of this ellipse is basically a function of the only other dimensionless number in town, the vorticity divided into the shear of the flow. Okay, so this is what the equilibrium solution looks like. As you increase the shear, right, compared with the vorticity, this thing just gets stretched way out. So you go way, your Lx it increases like that. As you make the vortex bigger and bigger and bigger in dimension, it becomes rounder and rounder. There's a point where it's unity. There's an unstable branch over here. Okay, but basically, the shape of the more shear, the more stretched out is. We've looked at that for non-uniform vortices, for 3-dimensional vortices and Boussinesque flows, for 3-dimensional vortices and anelastic flows. There's some corrections in QG. Things depend upon the area and LR. But basically, that's the right shape. You can make small corrections. But that really is the horizontal aspect ratio of a vortex embedded in shear. Okay. If I take the shear of the zonal flow asymptotically far from the red spot, and I measured my potential vorticity there, it should be stretched out by about a factor of 5. It's about 1.5 here. This is about 1.5 times that distance. The shear should have stretched the heck out of this thing. Why doesn't the shear stretch the heck out of this thing? And it's answered in this graph. So this is very simple. I just used 3 contours to make it simple. This is latitude. This is asymptotically far away from my vortex. This is the potential vorticity, right? So this is where it goes. It goes from a large decreases, becomes large again because it's got that reverse over there. The velocity produced by this guy looks like that. It puts a lot of shear on my anticyclonic red spot. Here's the red spot itself. The red spot itself, if I look at go right through the center here, if I go right through this and plot the east-west velocity through the center, I get this, a fair amount of shear there, self-induced shear. This little part over here makes the shear actually go slightly backwards. And when I sum them together, right, with this equilibrium solution where I've got this displacement now of the jet going around it, the shear here is not the sum of the shear here and the sum of the shear here. And the reason is the following. By putting the vortex here, I took this contour and I deformed it upward. I moved some of this light gray potential vorticity into kind of a half moon like that. And when I pushed it downward, I moved some of that light gray potential vorticity down like that. So the 3 effects that control the total shear are the shear due to this guy, and then their interaction. This guy interaction is in the opposite direction and nearly cancels that shear. And the reason that happens is because, right, these guys are also going to be anticyclonic, the way it's set up. And so this produces a velocity around this. This guy produces a velocity around that. So I've got a velocity whoosh, like that acting on it. That's producing this. So it's these deformed things that produce that. If I didn't have a potential vorticity jump here, if those were just streamlines, I wouldn't produce that. And then the red spot becomes really elongated and breaks apart. So it is absolutely essential to have, for the right aspect ratio, to reduce the shear where the red spot is located, and this is one way of doing it. I'm not saying it's the only way of doing it, but this is certainly one of the effects that it has. It permits me to have red spots with the right horizontal aspect ratio. There's some other piece that's kind of cool here. Let's skip that. The red spot is hollow. The red spot does not have, it's not uniform potential vorticity, right? To our best analysis doing this stuff here, the potential vorticity is at a minimum at the center. It's down by about 36% plus or minus 5% from the vorticity in the potential vorticity in the collar. That's bad news. Even with vorticity, you can easily do this experiment. You can do it analytically. You can do it numerically. Here is vorticity. Yellow has less vorticity, potential vorticity as you go oranger and redder. So this has got a minimum at the center. And these guys are unstable. So if I do that, it turns itself inside out. It doesn't destroy itself because shear likes to keep things together, but it reassembles, so the potential vorticity monotonically more or less decreases from the center outward. Okay. I now change my bottom topography the way my contours told me to do it. And I only kept one in just for illustration rather than two nearby ones. This is our hollow spot, but it's interacting with a zonal flow with a potential vorticity gradient. By pushing this blueness down over there and making this black, the effect of that is to decrease the shear in the center. It's the shear in the center that makes it want to go unstable. So when I now do this is pure QG, nothing fancy at all. This is stable. If you try and build a red spot and you don't have potential vorticity gradients around it, you will not get a hollow vortex to be stable, and you will have the wrong aspect ratio. Those are qualitative features that back up this quantitative analysis. If you don't have those, I can't build you a hollow red spot.
You don't literally mean hollow. You just mean
yeah. People in the literature, they started with just vorticity. In fact, this is like Lamb or somebody said, if you've got a minimum vorticity at the center, he called it hollow. And then, so I just kind of took the term over.
Okay, and this is only stable for assumed deformation.
This is,
this configuration.
Pardon me? This
configuration is only stable for assumed deformation radius of 2,000 kilometers.
Yeah, I mean, there is a window of deformation radii, depending upon the area where this will lose stability, right? This is somewhat fragile. Yeah.
Phil, do you have a interpretation for where the hollowness comes from? Is it a decreased vorticity? Is it a column height thing? Is it?
The short answer is no, because most of the other vortices on Jupiter are not hollow. However, in a completely different side of my brain, we've been working on vortices, three-dimensional vortices with anelastic and Boussinesque, not 2D, in protoplanetary disks. And we get sheets of big PV jumps where you've got a lot of cyclonic sheets. All the vortices are basically hollow there too. I'm not exactly sure. Understanding why something is stable is not the same as understanding why it formed in the first place. So the answer is I do not know, but I would like to investigate that.
Is that a natural consequence of QG?
I'm sorry, is what?
Isn't that a natural consequence of a QG vortex?
No, because the white oval is incredibly uniform potential vorticity.
But that's about the size of the deformation.
No, the deformation radius there is not that much bigger than it's in the high 2000s, and the principal diameter of the oval is about 10,000 kilometers. So it's not that much of a difference. And I was really, really surprised. I mean, it is so flat, the potential vorticity. I mean, what we did, and the way we did that is we said, well, we've got contours that's inside a potential vorticity. Basically, by removing all the contours and having only one outside one, we got basically within the observational uncertainties. So, yeah, I don't know. I don't know what makes it. Okay, so let me do a couple. Oh, we're running out of time here. Okay, a couple things about anticyclones and cyclones. So there was this comment that Jupiter has lots of anticyclones but no cyclones because they saw regions that they thought were cyclonic, but they were these filamentary things. And the arguments was, well, no respectable vortex would have streamlines that look like that. We call them filamentary patches. But in my junior mechanical engineering course, we do the difference between a streamline, a streak line, and a particle path. They're only stay the same when you have a steady flow. So this is where the particles are moving, which has nothing to do in a chaotic fluid. Really, really nothing to do with where the streamlines are. So it can be very deceiving. So I want to show you a couple quick things of this. So most of the vortices on Jupiter occur in rows. The red spot's unique. There's only one of them basically at that latitude. So let's just say, okay, so long time ago, I wanted to make a row of anticyclones because at 41 degrees there are 12 anticyclones, and I wanted to make them numerically. I wanted to simulate them. And I ran into a problem. So they're sitting in an anticyclonic shear, and you got an anticyclone here, and an anticyclone here, and an anticyclone. So I made them all the same size, all the same shape in equilibrium. But if I perturb this guy up just a little bit, right, these anticyclones, they go with the flow due to themselves, and background has more or less uniform potential vorticity. They just advect with the background flow also. So you pick this guy up. The vortices, his neighbors, are going to make him move to the left. This guy's going to make him move more to the left because he's in this region. And these two guys merge together. And very quickly, everybody merges together. So I was really flummoxed. And the only way I could figure out how to do it was to put him in a Kármán vortex street and say, okay, I've got a cyclonic region over here. Let's suppose I've got cyclones going around over here. Now, let's pick this guy and lift him up. He starts moving in this direction by the shear, but this cyclone moves him downward, right? He's downward under the influence of this guy, and he orbits stably around the center. Okay? So numerically, you can with point vortices, finite vortices, really ragged-looking vortices. These are the Kelvin-Helmholtz. The Kármán vortex streets are very, very stable objects. And you can't have them unless you've got cyclones. So I think that cyclones are there, but just much harder to see. Okay. And also, it's interesting because it might explain why there's only one red spot. So here's, if I'm at 41 degrees, right, here I am. Towards the equator, slightly south, I've got my cyclones sitting there. My next row would be 34 degrees. I've got 3 anticyclones there, 3 cyclones in between. But if I'm at the equator, and here's a red spot, when you get north of the red spot, it doesn't look anything like two-dimensional flow. It looks like really upwelling three-dimensional turbulence. So if I can't produce north of the red spot, if I can't produce shepherding vortices somehow, then because it's so turbulent in 3D, then I'm only going to have one red spot. Maybe. Okay. Hypothesis. Okay. But there's another thing that a student of mine did. We put this in a piece of Nature somewhere. These vortices tend to be shielded, right? Everything you do, they're very shielded-looking vortices. Maybe a picture of that. Yeah. So basically, these are compact vortices. So in 3 dimensions, when you actually do these, or if I've got a blob of potential vorticity here, they're not barotropic lines. The vortex lines just don't go to plus or minus infinity and get tangled up. They close on themselves and make a dipole. So what's going up here is going down here. So if this is anticyclonic here, it's got a cyclonic ring. So these are very fully shielded vortices. So there's an argument that you get, when it's anticyclonic, you get upwelling, and when it's cyclonic, you get downwelling. And people have argued that if you can get the velocities, the heats, the phase transition heats. When you're upwelling, you're going to cool things off and make ammonia crystals. So when you look at the clouds, they're mostly made out of ammonia. When you're downwelling, you're going to melt them. So this is a creation zone. This is a death zone. If I had a, quote, cyclone, which would be cyclonic inside, death zone inside, creation out there. So all we did was we simulated a Kármán vortex street. QG, completely degenerate in the dynamics between cyclones and anticyclones. But the particle tracers weren't degenerate. We made them proportional to whether it was how anticyclonic it was, and melded them proportional to how cyclonic it was. And these are the particle tracers. And right, there are ammonia, right? Here is where schematically the anticyclones that were shielded were. Here's where the cyclones that were shielded. Basically, what happens here is that here's what Jupiter looks like. Anticyclone, surrounded by a dark kill zone. Chaotic, messy-looking cyclone. All right? Another anticyclone, bright, elliptical, death on the outside. Here is the PV of our simulation, black and white. Here's the vorticity of our simulation. So we're creating where it's black and destroying where it's white. It's really chaotic here. So in the chaotic region where they're being formed, you get these filaments. All right, so I can't prove that that's what's happening on Jupiter, but you should not trust cloud patterns to make statements about whether you've got vortices or not. That's the lesson I want to get across.
Same thing would be true on the Earth. I mean, all the highs are all cloud-free, and all the lows are chock full of clouds. I mean, if you look from space at the cloud cover, you can't see the high pressure signatures.
There are a number of funny differences between the Earth's, the working fluid on Earth, right, is water, so H2O. So that's more buoyant than the surrounding thing. This is ammonia, which is more dense than the surrounding. There are a lot of differences because of things like that.
I'm saying it's not a surprise that cloud physics are what you can detect.
Yeah, okay.
Exactly.
But people...
Yeah, exactly, but you can't see them.
Okay, so a couple quick things, and I'm over. One more thing, and I guess I'm not going to get to 3D. After all these things are preserving rows of vortices, 3 white ovals that have been around since 1933 merged together. 2 of them merged together in 98, and in 2000, those 2 merged together to form 1 white oval. Why? How did it happen? So there were a lot of papers that came out on Icarus talking about vortices merging. Well, it's not vortices. Vortices merge unless you have something to prevent them from merging. The question is, why did, it's not, you really want to understand what was the difference between the shepherding cyclones. What changed here? So here's what I think changed. Here are 2 anticyclones and a cyclone in between them, though it was reported in the literature that this was an anticyclone because everybody knows you can't have cyclones on Jupiter. All right. So here's a picture of a simulation, and I gotta blow it up this way so you can see what's going on. This is an old simulation. I apologize for the low quality graphics, and it's QG. And here are 2 anticyclones. What you can't, uniform potential vorticity. The shear goes back and forth along with the bottom topography, and these guys are being repelling each other, so they're trapped. So this vortex is trapped, and here, of course, it's pushing this guy out. If there were another blue anticyclone here, then this guy would oscillate back and forth. And that's what you really see on Jupiter if you go back 100 years. You can see the vortices, and because you can't see the cyclones very well, the anticyclones kind of drift along, and then suddenly they reverse direction. And goes, what happened? What happened? Well, you probably couldn't see the anticyclone very well. Okay, so you're all familiar with this. When you got nice jet streams, right? Nice jumps in potential vorticity, you can trap vortices in there, right? It happens all the time. Okay, so on Jupiter, you can trap anticyclones. Here is a jump in PV. It's more cyclonic here down below than it is above it. So these shoulders act like kind of virtual cyclones. So these guys are repelling each other. But you can put more than 1 egg in a basket. It's a fragile basket, but you can do that. Okay, so before the vortices merged together, right, you found that triple that I showed you wandered around for 1.5 years on the planet, really, really close together. Right? So what would explain that? Well, this would explain that. Here's a simulation. Now, where I put in my Jovian potential vorticity, so the color is the potential vorticity. This is my jump in potential vorticity. I'm more cyclonic down here, so it's bluer than the blue here. These guys look like virtual cyclones. And so I've got a basket full of 3 vortices, 2 anticyclones, and 1 cyclone that go along in my basket. And these will travel like this, basically indefinitely in this calculation, or until I run out of computer time. This guy just goes back and forth, and the little trough goes on. And he's all happy. But it's fragile. So now let's put in a little bit of reality, more vortices. Same calculation, but now I've added this guy over here. This guy's going to come and approach us. He's going to upset the eggs in the basket, right? So he just did a little bit of impart momentum to it, and blotto, merger. So this really consists pretty reasonably with the qualitative pictures, except for the misidentified labels. So in fact, this is a picture from that calculation, right? Here's the cyclone kind of distorted. This is a picture appeared in the New York Times just before the merger. I would argue that this is labeled a cyclone. It's an anticyclone. Okay, so I see that we'll just sort of skip through everything else. And so if there had been more time, I would have told you about boost-and-esque things. There's certain things that you can't do with QG, like getting heights in the vertical direction accurately. And you also can't get, with the QG calculations, I put in a thermal dissipation of 4 years. Everything dies in 4 years. When I do that in boost-and-esque, I can get a red spot to last for 800 years. And it's a very subtle thing. It produces this very weak secondary circulation. And the energy that's compensating is being brought in by that circulation. And the physics is kind of fun. If you think about our atmosphere, if you were to take every molecule in that atmosphere and just drop it a centimeter, you would unleash a huge amount of potential energy. That's basically what the secondary circulation is doing around Jupiter. It's dropping, it's trying to destratify the atmosphere, and by that it's gathering energy. Okay, better stop.
So you just convinced me that it was harder to see cyclones because of the tracer effect, and then you showed this beautiful picture of 3 vortices where the cyclone was perfect.
Because it's clear that the morphology, when an isolated cyclone, if it's sitting in a chaotic region, it's going to have lots of them. But in this region where it's shepherded by 2 strong anticyclones, the velocity is very different. It doesn't have that nice chaotic pattern to it. And so you would expect the morphology to be influenced by the neighbors.
The upwelling and downwelling is
yeah, well, there's some change in the upwelling and downwelling, but it's just when you calculate that little basket of things, and I look, the flow is much more laminar than it is when I've got an oscillating Kármán vortex stream. So I'd expect the morphology to be very sensitive to its neighbors. But it is a question about, I mean, once you go away from QG, cyclones and anticyclones are really different objects. When you have an anticyclone, right, the atmosphere around it's stratified, but inside the anticyclone, it's less stratified. But for a cyclone, it's got to be more stratified. It's got to be super stratified. There are many, many things by mixing that unstratify stuff, but there are not that many things in nature that super stratify stuff.
But so that, in that calculation that you showed with the 3 vortices that coexisted for a while, if you had put in tracers in that with the same dependence on the cyclonicity as before, would you still see the tracer field?
I don't know. I haven't done it. I don't know. That's a good question.
So I just follow up on these questions. Does this mean that this is sort of resolving this great debate that was some 20 years ago about the cyclone, anticyclone asymmetries?
I think it sheds some light on it, but I don't think it solves it. I mean, we've been thinking, we've been daring to think about oceans and cyclones, anticyclones, and in the laboratory. So I spent 3 months trying to be a laboratory helper, breaking things mostly, in Patrice Legal's lab in Marseille, where he's got a 1 meter rotating tank. It's stratified, and we were looking at this, cyclone, anticyclone. There's a question of, is it non-degenerate because of survivability, of what's more robust, what's unstable, or is it just harder to make? It's certainly, as I said, a lot harder to make cyclones decently in the laboratory because you've got to find some mechanism to superstratify the flow. It's so easy to destratify it by mixing. So I think there are a lot of things that go. I don't think there's one silver bullet for that. I think some of it is detectability by clouds. I think some is just the robustness of them due to finite amplitude instabilities, and I think some are easier to make than others.
But I think that's a very barotropic, or at least equivalent barotropic perspective. And baroclinic fluid is pretty easy to end up with cyclones on the top and anticyclones in the bottom.
So how do you in the lab? All right, suppose I go in the lab.
So if you have a stratified flow with a shear in it, you'll get streets of cyclones and streets of anticyclones.
Right.
In the vertical, they'll be displaced from one another. And so depending on how you set up that initial sheared in the vertical and horizontal flow, you can end up with all cyclones at the top or all anticyclones.
Okay. So I should get a reference on that because I'm really trying to get my pals to make cyclones and anticyclones for looking at zombie vortices and things.
Yeah.
So that I'd really like to hear about it, because we've been injecting salt water, we've been sucking out salt water, we've been twisting things. It's kind of a messy thing, and it's not so easy to numerically simulate, right? Because you got to worry about that. You really want to be in the lab doing it, and so there's like all recipe books that we're trying to follow.
The major problem is always, of course, the forcing and the dissipation for systems. So by putting no dissipation, you don't need any forcing. But these things are strongly dissipated. They have to be forced. So are you arguing for a convective engine of some sort?
No. Okay. So when we do, all right, we've done Boussinesque and to a much lesser extent anelastic 3D of our red spots sitting in shear. Okay, and we put in a time scale, so that a thermal time scale that said, okay, the density of these things that are keeping these things in equilibrium, that's going to die in 30 turnaround times. And yet these things last 40 times longer than that. And the way they're getting their energy, like I say, is through their secondary circulation, weak as it is, it's harvesting. So if I look at the secondary, there are 4 fluxes that in the Boussinesque. There's a kinetic energy flux, there's an enthalpy flux, there's a potential energy flux, and there's a flux that I don't know what the name is. It's the it's the Brunt-Weissler frequency times Z, basically divided by G, the quantity squared. Okay, and that flux, that one's the biggest one. And what that one does is inside, right, so I got a red spot, and it's trying to be an equal. It's got this high pressure center, and it's got to have this high density lid above it. But the high density lid is fading away due to radiative transfer. And so it's out of equilibrium locally. So the high pressure here starts an upwelling at the center and a downwelling here. And it goes past the vortex, outside the vortex, and comes in. So what that does is that upwelling takes entropy or potential density, and the stuff that was lost by radiative dissipation, it replaces that potential density by the upwelling over here. But outside in the circulation, in the broader atmosphere, it's taking heavy potential density and it's bringing it down, and it's taking light potential density and it's bringing it up. So the atmosphere around it, right, is releasing all that energy, and it's being harvested by the secondary flow. Right? So we've actually calculated that numerically. And so the forcing, right, that's eventually going to just by radiative balance, right, because that's a force dissipative system itself, right? What's keeping the temperature is, a balance between what's being lost by radiation, what's by internal heating from the sun. So that's a vast source of energy. But basically, it's giving it just almost at the right rate due to what you're losing by the thermal losses in the red spot. So it is a force dissipative system. And we were really smart. But it turns out,
on forever or just 800 years?
We've only got it to go for 800 years. And we don't know how all right, there are people that claim that, let's say, I once gave this talk at your institution, that the Great Red Spot's older than Harvard University by about 2 years, right? What year was Harvard? 1635?
Did you actually see when it formed?
No, Hooke was the first one that saw it. Hooke, in volume 1, number 1 of the Royal Philosophical, right? Hooke, and they're very gentlemanly in those days, and no women, I'm sorry. And the great Mr. Hooke is reporting on his 10-inch telescope, not 10-inch diameter, 10-inch long, and he reports on the red spot. 2 issues later, Cassini said, I saw it first. So these quarrels go all the way back. Some people think that that's the same red spot that we see today, but there's like a 200-year gap where nobody mentions it. So maybe it disappeared and came back. It's been continuously seen since just after the Civil War.
Don't forget Jovian in the 1640s is also claimed to have seen the red spot.
Pardon me?
1640s Jovian, he's also claimed to have seen the
Right, I mean,
red spot then. I mean, he's been.
I saw dark
Jovian
energy first. Yeah, it's,
Well, it's not 800 years.
No, it's not 800 years. But QG simulations will show these vortices being stable for thousands of years, even more.
Without dissipation.
I mean, there's some dissipation.
It's no problem getting things to last for a long time without dissipation.
right, so
You have to be a force dissipative system. You have to balance these two things. you have a steady state, you have to do as much forcing as
Right.
dissipation.
Are you talking small scale dissipation or large scale dissipation?
I'm saying that if you it's not enough to say I have a Jacobian zero solution. You have to explain how that particular Jacobian zero solution is forced enough to make up for its dissipation. If you don't put any dissipation in, any Jacobian zero solution is pretty fine. That's like playing tennis without a net.
Right, but are you thinking of dissipation on a large planetary scale, or you're thinking
The great red spot is under discussion.
Right, so we think that the radiative dissipation is the fastest time scale, because just from the fact that people have talked about, you're going to get dissipation due to Rossby radiation. None of our numerical simulations show that once you've gone through the transients and the major axes of the vortex are aligned with the shear, we never see Rossby waves being launched. We don't see energy being lost by that. And there's a bit of
on a beta plane.
On a beta plane. Or on a beta plane where there's any kind of potential, right, bottom to top, as long as you have a potential gradient, you can get Rossby waves. But we never see that. We never see, in the QG calculations, we always see these things die on the thermal time scale. They never last more than the thermal time scale because it can't do this secondary circulation thing. And in terms of, there's turbulent erosion and things like that, it's a funny business. It's stratified. It's rotating. There is a very strong inhibition going down to small scales. Things that start to small scales, they want to reform. Lots of vortex. Right? Vortex merger is not in itself reverse cascade, but it certainly can lead to reverse cascade. But there's a lot of reverse cascade going on in these processes in 3D.
And remember, the large scale, radiative time scale is the contact level on the order of 3 years, so 3 to 5 years. It's pretty long. But there's very little dissipation at the contact level.
I had a couple quick questions about the stratification fill for the 3D simulations, especially the inelastic. So what's the rough density scale heights across the domain?
Oh, okay. So let's see. So
Ballpark.
Ballpark. So when we do the inelastic calculation, the pressure scale height is about 21 to 26 kilometers, and the density scale height is within 50% of that.
And how big? How tall are you?
So how tall is the vortex?
How many density scale heights are you spanning over the whole system?
Order 1.
Oh, just order 1.
Right. I mean, these are pancakes, right? The part that I didn't get to is what sets the height, right?
Yeah.
The height of these guys, by kind of various measures, is again about not that different than 1 to 2 pressure scale heights. So we're talking 50 kilometers compared to 26,000 kilometers. They're pancakes. They really are.
And are they stably stratified?
Yes, they are. The Brunt-Weissler frequency is extremely. The Brunt-Weissler period is about 12 to 15 minutes at that attitude, whereas it takes 10 hours to go around. So it's a very fast time scale, and it's very stably stratified. And okay, so you can infer for a couple reasons. You can infer the stratification inside the vortex. It's not the same, but people have measured now. It must be a dozen people have measured the temperature at the top of the red spot versus the top of the red spot at the center and the side. So that delta T over T will give you the difference between the Brunt-Weissler frequency inside and outside. There's some funny interpretation because there are methane clouds and other stuff. So you've got to do a little bit of closing your eyes and doing some radiative transfer to get those numbers out. But people see it's been consistent since 1979 what the numbers are getting for this.
Okay. Bobby, do you have a question?
No, it's getting late.
Yeah. Okay. I just want to make a final closing comment. But first, let's thank Phil for doing this.